This video is for Module 2, Part 4, and will include a discussion of the WSU vitamin study. Okay, let's go ahead and get started. The WSU vitamin case study is a study that was done here at Winona State. It is similar to the breastfed bottle-fed case study in that a matched paired study design was used. In the WSU vitamin case study, individuals were matched against themselves. Also, summaries needed to be computed before a two alternative choice model could be used. So let's go ahead and take a look at the data. These sets of notes may take a bit longer to load as these Google Docs are integrated within the set of notes. It takes a little bit for those various Google Docs to load. So this is a Google Doc here that shows the original data. There's a link provided if you want to download that Google Doc. We're going to worry about or investigate the vitamin A, outcomes from vitamin A. This study actually included outcomes for calories, vitamin A, vitamin C, calcium, iron, etc. But we're going to look at vitamin A, and we have two columns for vitamin A. We have the actual intake, so this is a amount, it's actually an average amount of vitamin A taken in per day for that particular individual. And then we have the vitamin A DRI, which is the daily recommended intake. So we have a daily recommended intake for each individual in the study, and we have an actual intake of vitamin A for each individual in the study. Now the daily recommended intake, it looks like on the screen, is around 700 for many of these people, but there may be certain diet restrictions or other considerations where somebody might have a different daily recommended intake for vitamin A. So when we're doing this analysis, we want to compare for each individual whether or not or how close their vitamin A intake is to their DRI. So that's the matched paired part of this design. And they're actually being compared against themselves because I have an actual measurement and also a daily recommended measurement for each individual in this study. Now, in order to use a two alternative choice outcome approach, we're going to have to get these measurements into one of two choices. And what I've done here is just identified for each individual whether or not they were over or under on their vitamin A intake. And I can use a simple if statement in a spreadsheet to accomplish this. So the statement that I used here in column J was just equal if H2 is the actual vitamin intake for that first person. So I'm going to compare their actual vitamin intake against I2, which is their daily recommended intake. So this statement right here, that if H2 is bigger than I2, is just checking to see if the actual intake is bigger than their daily recommended intake. If it is, I'm going to identify it as being over, and if it's not, I'm going to identify it as being under. So let's come down here and look at patient 5 here, row 6 of our spreadsheet. But that's patient 5. You can see that this individual took in 164 for vitamin A. They should have been taking in about 700, so that individual was under what they should have been taking in. So this column right here, column J, is just identifying whether they were over or under their daily recommended intake. And that's going to be my two alternative choice options here, or outcomes, the over or under. The next step then is to simply count up how many overs, or I could count up how many unders I have. I chose to count up the number of overs, and I'm going to do that for the females and males separately. So our analysis here is going to be done for the females and then again for the males. A COUNTIF statement is used to accomplish this. I am counting the number of overs in cells J2 through J58. So J2 here is the first outcome for that first person in the study. It's in the second row, column J. If we go down to J58, you will see that is where the last female was actually listed here. So if we go way down here, J58, so again that's row 58 in the table. It's person 57, but it's in row 58. That was the last female. So I want to count up the number of overs between cells J2 and J58. And then I'm going to count up the number of overs in cells J59 through J72, and that will be for my males. We can quite easily see here that that's just 3. So I have 3 males that are over on their vitamin A intake, and I have 25 females that are over on their vitamin A intake. And those are going to be our 2 study outcomes that we're going to use for our analysis. So here those are, just in a different table, shown with a graphic as well. For the females, for vitamin A, my observed number that were over was 25, and the number that were under would be 32. The left-hand side here is for females, and then the data for the right-hand side is for the males. All right, so let us consider the research questions that will be used here. So the research question being posed here, is there enough evidence to say that WSU females are off target from their daily recommended intake for vitamin A? So by off target here, what we mean is, do WSU females deviate from their daily recommended intake of vitamin A? That same research question is going to be asked of males as well. Is there enough evidence to say that WSU males are off target from their daily recommended intake of vitamin A? So we're going to do the analysis for females and males separately. Now the reference distribution will be set up under the situation that they are on target. Remember, the research question is what gets put into the alternative hypothesis. The null hypothesis is how the research question is, the null hypothesis is how the reference distribution is going to be built. And that's going to be, what would it look like if they were on target? In other words, what would it look like if WSU students were taking in an appropriate amount of vitamin A? So the parameter here is going to be set up at a 50%, because if an individual is on target, then there is an equal chance, a 50-50 chance of being over or under on their daily recommended intake. So the schematic for females is going to look as follows. The smallest number is going to be 0. The largest number is going to be 57. Again, I had a total of 57 females in my study. The parameter value is going to be set at 50%. And again, this is the distribution of what it would look like if the females were on target. They should be halfway up this number line. That expected outcome there is half of 57, which I think is 28.5. I need to check whether or not the outcome from the study is an outlier against this reference distribution. And from here, it doesn't look like it's too far off from the expected, so I do not anticipate it being an outlier. How about the schematic for males? Well, there were only 14 males in this study, so my number line is going to go from 0 up to 14. Halfway up the number line is going to be where they're on target. The study outcome for males was down here at 3. So again, that's somewhat further out away from that reference distribution, at least it appears on the way that I have drawn here. Now in each of these are going to be a two-sided test, because I could be off target by having too much vitamin A, in which my study outcome would be very, very high on the number line, or I could be off target by having too little vitamin A, in which case I would be an outlier on the left side. So the analysis, or the type of test that we're going to be running here, is a two-tailed test, because both extremes would provide support for the research question in suggesting that the individuals are off target. So we're going to run a two-tailed test for the females and also a two-tailed test for the males. Okay, what does the testable hypothesis look like in each case? Well, it's going to be set up under a 50-50 scenario. So that's going to be the case for the females and for the males over here. As just discussed, the type of test is going to be two-tailed. When we're determining values as extreme or more extreme than the study outcome. Okay, so let's look at the females first. So that's going to be the values from 25 and lower. 25 and lower. That's going to be the values on the lower end of the distribution. And then to figure out the values on the upper end of the distribution, what I need to do is look at how far away is 25 from the expected. And that's 3.5 away. So when I'm trying to figure out values as extreme or more extreme on the upper end, what I need to do is go 3.5 away on the upper end. So again, the expected here is 28.5. If I add 3.5 to that, I'm going to get a value of 32. So the mirror image of 25 in this distribution is 32. As I've explained this earlier, if I take this distribution and fold it in half, about this line right here, 25 is going to end up over here on this side at 32. So when determining values on the upper end, I need to start counting at 32, 33, 34, all the way up to 57. Likewise, for the males, the study outcome is 3. So values that are as extreme or more extreme on the lower end are just going to be 3, 2, 1, and 0. On the upper end, again, that distance between my observed outcome and the expected outcome is 4. So I need to go up to 11 here, because 7 plus 4 is 11. So values that are as extreme or more extreme on the upper end for the males are going to be the values 11, 12, 13, or 14. So when computing the p-values, I need to get the proportion of dots that are 25 and less, and also 32 and above. For the males, I need 3 or less, and then I also need the 11 through 14. All right, before we compute the p-values, let's just consider the following alternative explanation to a rationale in conducting a formal statistical test. So let's look at the females for a minute. The expected number of females who are over would be 28.5 when the females are on target. Okay, so I've drawn another graph here. So the expected number when they're on target is just going to be half of that 57. So 28.5 should be over and 28.5 should be under. So this here, what I have drawn in the right column there, is what it would look like under no difference. We'd expect about half of them to be over and half of them to be under. So the light gray here is for over and the darker gray is for under. Now what actually happened was I got a breakdown of 25 and 32, which isn't quite the 28.5 and the 28.5. Now this on the left-hand side is my observed data. Now the observed number, let's go ahead and look at this statement here. If another group of WSU females were selected to participate in the study, then the observed number is likely to change. That observed number should be close to 25, but it would change if a different group of WSU females were selected to participate in this study. So what I mean by that is this 25 value here and this 32 value is going to change if I were to go get another group of WSU females. And what we say is that there's going to be variation in this number. This number is going to change sample to sample or group to group that I might select to put in my study. Okay, so what a statistical hypothesis test is going to try to do is evaluate the likelihood that the overbox from the observed column, which we know is going to vary from sample to sample, is going to be statistically different than the overbox from the expected column. So do I anticipate, or how likely is it that this box on the left, the observed box for over, is going to stay away from or be different than the observed box over here on the right? Now you can see that these two boxes are about the same height here. They're pretty similar to one another. So as I've noted earlier, I don't believe that I'm going to have enough evidence for the research question. They look like it's pretty much on target. On the other hand, for males, I only had 3 males that I observed that were over. I should have seen 7. So there's a pretty big difference here between this gray box and the observed side compared to the gray box on the expected side. So I anticipate that I might have enough evidence for the males to say that they are off of target. But we'll have to conduct our statistical test and figure that out through the use of the p-value. The other important thing here is just this last bullet. A statistical hypothesis test takes into consideration the sample-to-sample variability that exists in a statistic. So again, this 25 count or this 3 count that I'm using in my investigation is a statistic. So a test takes into consideration that sample-to-sample variability. This fact allows a statistical hypothesis test to expand the scope of inference from the individuals in the study to, more generally, in this case, WSU students. So after I conduct a valid statistical hypothesis test, I get to expand my scope of inference to include not just the individuals in the study, but to the greater population of WSU students. Okay, a couple of definitions. The sample-to-sample variation is just the variation that exists in an outcome over repeated sampling. And then expanding that scope of inference, that notion, if individuals are selected randomly to participate in a study and a proper statistical test is conducted, then the scope of inference can be expanded to the group from which these individuals were selected. So selecting randomly just makes sure that the people that we put in the study are representative of that larger group. If that's the case, and a valid statistical test has been done, you can expand your scope of inference from not only the individuals in the study, but the individuals in that larger group. Okay, let's get back to obtaining a p-value for females and males. Let's go back up here and just recall what we have here. This is a 50-50 scenario. It's two-tailed. I had a total of 57 females and 14 males. So let's go ahead and use the app now to get the p-value. So this is a 50-50. For the females, if I do the females first, the number of tosses is going to be 57. And then just again get several thousand here, so I'll go ahead and get 5,000. This is going to be the distribution for females. So my study outcome for females was 25. And then I'm going to want to select two-sided as well. So 25 here is on the left side, so I'm going to specify left there. And then make sure these are two-sided or two-tailed. So we want to make sure and select that. The p-value then, that looks like what I get for my female analysis, is 0.4318. So let's go ahead and note that value down below in one of those text boxes, because that's what I'm going to ask you to do here, is obtain the p-value, provide a statistical decision, and write a conclusion. So my p-value is 0.4318. And again, that's for the females. Now this distribution is going to change for the males. So my number of tosses, or my sample size for males was 14. So if I change that probability of success or the number of tosses, the app is going to get rid of that old distribution because the distribution certainly changes. This one goes from 0 up to 14, whereas the other one went from 0 up to 57. So let's go ahead and get 5,000 here. My number as extreme or more extreme is going to be 3, because that's the study outcome for females, or for males, excuse me, was 3. And again, I want to make sure that it's two-sided. So the p-value that I get here for males is 0.0568. So I'll go ahead and note that below in the box as well. So those first set of boxes there are for females. Go ahead and just copy and paste this down into the mailbox. So here I have 0.0568. Now this p-value here is pretty close to the 0.05 threshold. The one up here for females is not very close at all. Remember, I need to compare this against 0.05. Don't compare it against 0.5, but 0.05. So for the females, it looks like I do not have enough evidence. So statement B is going to be the correct outcome here for the females. Again, what I'm doing here to make that decision, I'm just asking myself, is the p-value less than 0.05? And no, it is not. So when it is not, then statement B is correct. You do not have enough evidence. So maybe I should write no, do not have enough evidence for the research question. And that is statement B. Now I'll let you go ahead and write the conclusion. Remember the 3 different components there for the conclusion. For the males, I need to check whether or not my p-value, which is 0.0568, whether or not that's less than 0.05. Now, technically speaking, so maybe I can add in here a little bit. Technically, no, but it is close. So technically, do not have enough evidence for the research question. But again, the p-value obtained is close to 0.05. Close to saying we do have enough evidence. Okay, so here's a case where our p-value is really close to that threshold value there. But if we stick strictly to that 0.05 cutoff, then we do not have enough evidence. I'll let you go ahead and write the conclusion there for the males. There's 3 additional questions down here. Question number 5 there is to look at look at the outcomes for calcium. So the outcomes for calcium are here. Again, under a on-target situation, we would expect about 28.5. Females here are not very close to that 28.5. I only had 16 females that were over on their calcium intake. Whereas over here on the right for males, I had 8 that were over on their calcium intake. I should have saw about 7. So if I were to do an analysis here for whether or not we're on target, it looks like males are going to be pretty close to being on target, but females are not. It's pretty well noted that females do not take in enough calcium compared to their daily recommended intake. And that looks like it's also showing up in our data. So there's a pretty big difference here for the females between what actually happened and what should happen if they were on target. So I would anticipate that in the reference distribution for females, females are going to be an outlier, but in the reference distribution for males, probably not going to be an outlier. So I think it's reversed here from what I would expect or what we witnessed there when we did our vitamin A analysis. Okay, that does it for Part 2, Module 4, the WSU Vitamin Intake Case Study. Thank you.